Uh, Hello.
Yes.
Hello guys, can you hear me?
Yes, sir.
Okay, so we'll start the session. So there was a question regarding difference between PSLV and GSLV rockets, right? Uh, who asked this question? Who was the one who asked this question? Uh, yeah, somebody asked this difference between PSLV and GSLV. Let me see. Okay, so where is the in chat messages? Okay. So yeah, okay. So, anyways, uh, let me share the screen and share the screen. Okay. Yeah. I hope it is visible, no? Uh, I don't know why it is. Okay. It is. I hope you can see the complete screen, right? In my case, it is only the half portion is visible. Okay. Let me sync this part. Okay. So today we will start with these solid propellants. We'll start with the problem on solid propellants. So I hope if you have any doubts related to that, please let me know. If you have any doubt related to solid propellants, please solid rocket propellants, please let me know.
Sir, can you explain the heat released by the chemicals like QM in the lecture series?
Okay, so heat release. Okay, right. So we have seen that there is a block of solid propellant uh, which can be HTPB and ammonium perchlorate, right? So ammonium perchlorate is a solid solid part, and which is binded by a binder which we have as a STPB. Okay, STPB acts like a binder. Okay, to get the to okay, so what happens when the propellant is burned, the heat release, the flame looks something like this. So this is premix flame, and in between these two we will have a diffusion flame. Okay, so what exactly you have the question, can you please tell? So how the heat release is happening, what is the question?
The temperature equation that was formulated.
Okay, so that was d2t by dx square plus okay, so what we were saying there is, say we have a control, say we okay, consider we take a small control volume at this location. Okay, and what we are saying is, uh, say some of the products that are going in is m dot, okay, and the mass going will be conserved. Next is, we assume that specific heat at constant pressure is Cp, and this is at the C at and at the outside the Cp remains constant. It is not a function of temperature. At section X from the surface, we have temperature T, and at X plus some dx, we have T plus dt temperature, right? And in between this volume, we can also have reactions that are taking place, right? So say say there is CO plus NH2, uh, NH2, they can burn in this location, and they can also release heat, right? And these how like we have discussed last time, the chemical reactions, when chemical reactions takes place, we have bond rearrangement, and the difference between the bond energies is the chemical heat energy, chemical energy that is released, right?
Yes, sir.
And this chemical energy in turn increases the thermal energy, right?
Yes, sir.
So in this part also we can have some chemical reaction that can undergo, right? They can be quantified by q dot, which is say per unit volume, in terms of per unit, this q is, this is chemical energy that is getting released, um, that is some q dot into the volume of this control volume. Okay, did you understood?
Yes, sir.
Okay, so it will be something, if I define the coordinates, this is x axis, say this is y axis, and this is z axis, and we are only looking into, we are assuming that there is only a variation along x axis. Okay, there is no change along z or the y axis. Okay, so then if we take the energy balance, if we do the energy balance, what we will get is the, okay, one will be m dot cp t plus dt minus m dot cp into t. right? So this is what it is exiting, and this is the energy that is coming in. Coming in, okay, that will be equal to the conduction, basically. This is Ka. Okay, so if you take the conduction part, this the temperature here can be written as uh, yeah, so this is T plus um, dt over dx into dx. Okay, this temperature can be written as this part, no? 2x into dx. So plus the vol the heat that is getting generated inside this, right? So okay, so right, so area, this cross section area along this axis can will be equal to dy into dx, right? Dy into dz. So I'm talking about this area, right? So this part is because of the conduction. This part is due to heat, chemical energy that is getting generated. Okay, and this part is the enthalpy leaving minus enthalpy in. So if you substitute this, and if you write m dot can be written as density of the propellant into volumetric flow rate. Uh, so if you do that, what you will get is rho Cp dt by dt is equal to k uh, into, okay, there will be yeah, there will be another ka into 1 minute. So this is the diffusion part, no? So the Fourier's law of conduction says that we have plus, sorry, no tension, dt by dou x into dx, right? And this will be, so this will be d2t by dx square plus q dot. So what this equation tells you is the variation of uh, temperature along the along the so if you have x-axis denoted along the normal to the surface of the propellant, how the temperature varies can be determined by this equation. Okay, so this part in this is the chemical energy. This part is because of the conduction, and this part is the heat that is getting stored. Okay, okay, I think there will be some 1 minute. So yeah, this will be dt by dx, no, because it is t plus dt by dx into dx. So we have dt by dx, right? So this part you were having trouble, no? uh, who asked this question?
Yes, sir. Yes, clear.
So this is because of the chemical heat energy that can be liberated, or it can be absorbed, depends on the reaction. Okay.
So that's per unit volume, right?
It is per unit volume, yes. So it is something similar to what we have, I think, if you have learned about this conduction equation.
Yes, sir. Yes.
So it is similar to that.
Okay, sir. Clear.
Okay, so if you take the conduction equation, what you get is this plus q dot, it is per unit volume, no? And you have rho cp dt by dx. Why capital I have written this is this capital dt by dt, sorry. So this is, anybody's know what is the what does this means, this operator? This is the material derivative. So you might have learned about this thing in fluid mechanics, right? When you take the acceleration part, acceleration of a velocity, right? Acceleration using velocity. So you have u, so acceleration is given as u along x is du by dx, v du by dou y plus w. Correct, no? So you might have seen this equation, right?
Yes, sir.
So this part is known as convective term. This is convective acceleration, and this is local acceleration. So similar to this, we have dt by dx. Okay, so this can be written as u du by dx. Oh, sorry. So this is dt by dx plus v dt by dy plus w dt by dz plus dt by dt. Since we are assuming steady state, so this particular term will be 0. We are assuming that velocity along y direction, and x direction is 0. Y direction, z direction is 0. So this part and this part is again 0. Okay, so we are left with this part. So, and this operator, what anybody knows what is the meaning of this term? What does this term tells? What is the meaning of this term? Okay, this is Laplacian operator. So this is d2t by dx square plus d2t by dy square plus d2t by dz square. So we are assuming that there is no variation along y and the z direction, so this part is 0, right?
Yes, sir.
Okay, so again, so therefore we are left with so if you now see, you are left with dx square plus q dot is equal to rho cp, rho u cp dt by dx. I think we have left some. Okay, m dot is rho av, right? Okay, yeah, yeah. So if you do that, you will get some one u also here. Okay, so this it is the same equation that we have seen in Professor Ramamurthy sir's lecture. Okay, so anything else? Okay, if not, let us start with the problems now. So let us consider one this problem. So this is the burn rate R dot of a solid propellant grain follows the Saint Robert's law given by r dot is equal to pa to the power n. Okay, where p is the combustion chamber, p is the pressure in the combustion chamber. So which of the following is correct? So maybe I'll zoom it. So I would encourage your answers in chat box. Okay, so you can answer which of these options are correct. Any idea? So what do you think? What is the effect of N on stability of the rocket? And when we are saying stable, what is the meaning of the stable? Uh, any idea? Uh, it will be great if you can take part in the discussion. That will okay. So okay, who has written this? Maybe I'll start with him. So Shervan, so you say that if n is greater than 1, the combustion is stable. Why do you think so? Uh, okay, so n less than 1, huh? So why do you think so? So you can unmute yourself if you. Okay, so let us look into why what stability means in this part. So yeah, so consider a rocket engine. We have nozzle, we have propellant, right? So what happens if n is greater than 1? R dot increases as p increases, right? Which in turn tells that mass flow rate increases. It is correct, no? Because
Yes, sir.
m dot is rho of the propellant, area of the propellant, into the r dot, right? R dot is the regression rate of the propellant. Okay, so okay, so what we are doing is we are increasing the pressure, so mass flow rate is increasing, right?
Yes, sir.
Correct. So the pressure will increase. Okay, so since area throat we okay, so the area of the throat is fixed. Okay, and mass flow rate through the nozzle can be written as P naught AT and root T naught. Then there is some function of gamma and R, right? Okay, so and this should be equal to A P naught to the power n into area of the propellant into density of the propellant, right? To have the mass balance, right? So whatever we are burning, whatever we are generating here, that is this part. Okay, I'll mention as one here, this part, and whatever we are expelling out is this, right? In a stable system, it this should be the case, right? Whatever we are generating the gases, it should leave the nozzle. Okay, so
Yes.
what happens if there's a difference in these two? So what happens if the mass that is generated is less is greater than the what it is expelling out, what is going, what will happen, the mass will accumulate, right, in this chamber, right? So let us write the difference between these two will be equal to dm by dt, that is getting stored in the system, stored in the chamber. Okay, are you with me?
Yes, sir.
Okay, so now what is the phase of what is the phase inside this combustion chamber? uh, is it is it gas, liquid, or solid at this point? Say at point A, what is the phase?
Yes, sir.
Gas, right? So we can express m using p pv by rt, right?
Yes, sir.
Okay, so p naught at, I hope this derivation you have seen, right? Have you seen this derivation? Okay, this is fine, no? Okay, so again, now what we have to do is we have to integrate this equation. Okay, so basically what we are saying here is, okay, let us look into this equation what it says. Okay, so uh, okay, 1 minute. So it should be other way around, no? This is getting generated, this is generation, and this is um, nozzle mass flow rate, that is going outside the nozzle. Okay, so the difference will be the, if this is higher, generation is higher, the mass will be stored, right? So that it should be like this, the negative sign should be here, right? Okay, okay, so let us look into this equation. We have dp by dt, v by rt, a p naught to the power n, a p rho p minus p naught at by t naught, then there is a function of gamma and r, right? Okay, so if this term is greater than 0, what happens? dp by d naught increases, right?
Yes, sir.
Okay, if this, okay, if this increases, okay, if this increases, what happens to the pressure increases, right?
Yes, sir.
Pressure increases, this results in, again, the r dot will increase, right?
Yes, sir.
If r dot increases, again this part will increase, and there is a sudden increase in pressure. Okay, if n is greater than 1. Okay, if n is less than 1, so what happens, it becomes um, uh, as, okay, so this results in stable combustion. So if pressure increases, the burn rate will reduce, and the mass flow rate through the nozzle will be more, which will decrease the pressure. Okay, so in turn the burning will be stable. So Therefore, in this case, the answer is n is less than 1. For n less than 1, the uh, propellant will be burning in a stable mode. Okay, I hope this explanation is clear to everyone.
Yes, sir.
Okay, so or you can see through this equation again. So dt naught by dt 1 upon p naught. So this is a p naught to the power n minus 1 a p rho p minus, right? So now let us see this part. So what we are saying is how the pressure is changing uh, with this is just a normalized pressure, right? Normalized increased pressure. Normalized in the sense we are dividing by the initial pressure itself, right? So to to this thing to be greater than to be positive, this term p naught into minus 1, sh- this complete term should be uh, greater than um, okay, should be greater than uh, 1 minute. So yeah, so this part should be greater than this term, no? Okay, so and yeah, this part should be p naught n minus 1 um, should be greater than 0, should be greater than, okay, so yeah, p naught n minus 1, okay. Okay, let us try to integrate this maybe, then probably we'll get the answer. Okay, so let us assume this part to be constant. Okay, 1 upon p naught dp naught by dt. So this is some um, p naught to the power n minus 1, and let us consider this part as b, this is c, right? Okay, so probably it is not easy integration, right? P naught. Okay, so this is I don't think will come this. mm, okay, so for this dp naught by dt greater than 0, we have b p naught n p naught into c. So p naught n minus 1 should be greater than should be greater than c by b. Okay, so right, so this can be possible. Okay, um, yeah, so probably okay, I don't think this is leading to anywhere. So probably we can argue in this way that if pressure increases, if the burn then okay. So what we can do is we can argue in this way: if pressure increases, the R if R increases, so the mass flow rate that is getting stored within the chamber will increase, right? This can only be possible if n is greater than 1. So this is the unstable system. because this, if the pressure increases, then again the mass that is getting stored in the system is increasing. the the pressure will increase. This again will increase the r dot, and again the pressure in the system will exponentially rise, right? However, if n is less than 1, so if pressure increases, r dot decreases, dm by dt in the system decreases. Thereafter, what will happen? The pressure in the system will decrease. Therefore, pressure, if the pressure is increasing, so again there is a stabilizing mechanism, inbuilt stabilizing mechanism, okay, which is set up. So this is a stable system. Okay, so I hope this is clear to everyone.
Yes, sir.
Okay, yeah, okay. So let us look in. Okay, yeah, let us look into the another problem. So end burning solid propellant of grain 0 point, so length is given, and it is given a end burning grain. Okay, so how does a end burning grain looks like? So it is, so we have the casing, and then we have motor, right? And in this area we have the propellant. Okay, so if I see the cross section, it will be circular, assuming it, if it is a cylindrical. Okay, now what it is given is the length is given, so, and the burning period is given as 100 seconds when operating at a pressure of 2 megapascal. Increasing the operating pressure to 4 megapascal, the burning period reduces to 80 seconds. Okay, so we have to answer. Okay, and it is given that the propellant follows burn rate law given by R is equal to A to the power n, where R is in mm per second and P is in megapascals. So what we have to determine is, we have to determine n and A for the propellant. So would you like to give it a try? So I'll give you 2 minutes. By that you can try this question, second problem. So we'll have a discussion after 2 minutes. So if you get the answer, you can try to post it in the message box. Okay. So yeah, you can start now.
Sir, are these lectures recorded?
Yes, these lectures are recorded. Yes.
Okay.
Sir, where we can get these lectures recorded, like
Probably after 2 or 3 days, I'll upload it in YouTube.
YouTube, sir?
Okay.
Which channel, sir?
I'll give you the link. I'll share the link.
Thank you, sir.
Okay.
हाँ बोलो. मेरा है ए पॉजिटिव. क्यों? क्या हुआ? तो मुझे नहीं पता, मैं तो पॉजिटिव हूँ, ए प्लस हूँ. क्यों, क्या हुआ? सब सही है ना?
Sir, can you keep the iPad horizontal?
एक मिनट रुको रुको रुको। या कम अगेन।
Sir, can you keep that tablet horizontal? Because I'm not able to see the question.
या नाउ कैन यू सी, इज इट बेटर नाउ?
Yes. Yes, sir.
या यू कैन ट्राई नाउ। हाँ सब सही है ना?
हेलो।
हाँ सब सही है ना?
अरे हाँ नहीं, मैंने सोचा था कि वो बी नेगेटिव है, ये नेगेटिव है, तो मैं ये सोच रही थी, मैं मम्मा का शायद वो नेगेटिव है, अभी मेरा हुआ है।
मम्मा का कुछ और है, ए भी है, वो फालतू बोलती रहती हैं।
और डैडी का भी शायद ए पॉजिटिव है।
हाँ कुछ होगा, पता नहीं, सबका सब उन लोग का पता है नहीं, वो हवा में ऐसे ही बोल देती है, हवा में क्या कहते हैं, हम गलती से कभी किसी दिन गलत खून ले लिया तो लेने के देने पड़ जाने हैं।
मैंने
चलो।
भी इसी चक्कर में करा था।
वैसे भी क्या कहते हैं, खून चढ़ाने से पहले डॉक्टर क्या कहते हैं, ऐसे नहीं चढ़ा देते, ब्लड टेस्ट करते हैं पहले।
वही
चलो ठीक है।
थायराइड है, पहले एक पड़ा हुआ है,
बढ़ गया फिर से?
7 आया है, तो फिर से डाइट पे आना पड़ेगा।
चलो ठीक है, ध्यान रखो, मैं करता हूँ। हाँ पांडा बोल।
हेल्प चाहिए थी यार तेरी।
यार मैं 8 बजे आ जाऊँ प्लीज़, मेरा क्लास चल रहा है अभी।
सॉरी सर, चल ठीक है सर।
बता 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 क्या हुआ?
अरे नहीं नहीं, वो मेरे को बस रूम शिफ्ट करना था ना, इसलिए
सुन
चाहिए
सुन,
था।
8 बजे मैं बाइक लेके आता हूँ तेरे रूम पे।
अरे हाँ भाई, 8 बजे मत आइए, अभी मैं बाद में मैं थोड़ा लेट आऊँगा, 8:30 बजे तक आ जाऊँगा मैं यहाँ पे, 8:30 बजे आइए।
तू सामान सब कुछ रेडी करके रख ले प्लीज़, मैं 9 बजे फिर मैच है ना।
चल ठीक है ठीक है, 9 बजे तो रूम पे नहीं आना मेरे।
9 बजे? 9 बजे क्या हुआ है, क्या है?
नए रूम पे हम बकचोदी करेंगे, इसलिए मैं बता रहा हूँ।
मैं मैच खेल के आता हूँ।
चल ठीक है ठीक
ठीक
है।
है, क्या खाने के लिए क्या कर रहे हो?
मैं तो अपने उनके साथ ज़्यादा दोस्तों के साथ बाहर जाता, बाहर से वापस आऊँगा मैं, थोड़ा लेट हो जाऊँगा। इसके बाद इसका विकास और हम लोगों ने ग्रुप में सब ना, वो जो पुराना जो ग्रुप का पूरा ग्रुप है, तो वो लोग आएंगे, नया वाला जो रूम है उसको मतलब वैसे ही बकचोदी करने के लिए।
ठीक है, मैं पत्ते वत्ते कुछ खेलने के लिए, जेंगा भी है मेरे पास, जेंगा लेके आता हूँ।
हाँ अगर तेरे पास है तो लेके आ जाइए। चल ठीक है।
मैं आता हूँ, मैच के बाद आऊँगा 9:30 10 बजे।
कौन सा मैच है?
वॉलीबॉल।
वो तो ज़्यादा टाइम लगेगा, 10 बज जाएंगे।
हाँ देखता हूँ, मैं आ जाऊँगा ठीक है।
चल ठीक है,
ओके।
thank you।
हाँ,
चल
मैं शिफ्ट करवाऊँगा, ठीक है, आके मैं शिफ्ट कराऊँगा।
अभी नहीं, मुझे बस 2 चीज़ें शिफ्ट करनी है एक्चुअली, मेन काम मेरा गद्दा शिफ्ट करवाना है बस, और कुछ नहीं, और सब मैं खुद शिफ्ट कर दूंगा।
ठीक है, तू 8 बजे कहाँ है? 8 बजे कहाँ है?
8 बजे मैं बाहर गया जाऊँगा खाना खाने के
तो
लिए।
एक काम करेगा, सचिन के रूम में रख देगा, सचिन और मैं ले आएंगे।
नहीं नहीं नहीं, मैं ले जाऊँगा, मेरे 2 सामान है, मैं ले जाऊँगा। उसके बाद मेरे को दिक्कत होगी, क्या इतना बड़ा गद्दा ले जाने में।
ठीक है, तो मैं 8:30 पे आता हूँ, ठीक है।
चल ठीक है ठीक है।
ओके बाजी, बाय बाय। Okay, so anybody got the answer? Okay, so let us try now. Okay, so one more minute, please. Okay, you can try. Okay, I will start. So probably a few people have got the answer. So let us see. So length is given as uh, length is given as 80 mm. Okay, 80 mm, right? So where is the question? Yeah, it is a point 0.8 meters, right? And the time is given as for first case when the pressure is case 1, when the pressure is 2 megapascals, the R, which is the regression rate, is just L over T, is given as 0.80 divided by 100, right? And in case 2, we have pressure.
Should we make it zero point 0.8 into 10 to the power 3 to make it into millimeter?
Uh, yeah, yeah. R is okay. So R is in millimeters per second, right? Correct. So it will be 80 by 100, right? And for the case 2, when the pressure is 4 megapascals, the R dot is given as 80 by 80, which is 1, and this is 0.8. Okay, so now the R dot is also given as a 2 into 10 to the power 6 to the power n, and R dot is a R dot 1. Yeah, so this is okay, R dot 1, R dot 2, 4 into 10 to the power 6 to the power n. So if we divide these equations, we'll eliminate a, and we will get 1 by 2 to the power n, and we will have 0.8 divided by 1, right? So if you solve this, okay, so if you solve this equation, if you take log on both the sides, you will get, okay, so n is ln 0.8 divided by 100. Okay, so you will get this value as 0.3219. So I hope you got the same answer, right?
Yeah, 0.32.
Okay, so for a, what we have to do is, which is just uh, 8. Okay, this is we can substitute in either of the equation. So this is 0.8 is equal to, okay, 0.8 is equal to a 210 to the power 6 to the power 0.2219. Okay, so if you substitute this equation, so you should get the value as okay, this is 0.8 divided, okay, so you'll get it to the value as 0. 640. So how much you are getting, guys?
0.64.
0.64, right? It's correct now. Okay. So R is equal to 0.640 and P to the power 0.3219. Okay. So let us look into another problem now. So okay. So yeah, I hope you can see the problem, right? So we have end burning grain. Again, we have end burning grain. Okay, that uses double based homogeneous propellant called bellicite. The cylindrical propellant gate has the following characteristics. Diameter is given. Okay, then length of the propellant grain is given. Uh, and density is given 1750 kg per meter cube. Okay, and it is also given the burn rate equation is given, chamber pressure is given. So what you have to do is you have to find the burn time of the propellant. Can you do this? So what you have to do is, you know, R dot, right? You have L, that is over T. So if you calculate R dot, you will get the value for T, right? And that will be your burn time, correct? Then next thing is, what is the mass generation rate of the hot gases from the propellant. So how you will proceed to this? It will be m dot is the propellant area of the propellant into the R dot, right? So if you have an unburning grain, so this is the area of the propellant, and the R dot is just the velocity at which the surface is preceding, and rho dot is the density of the propellant. Okay, so would you like to give it a try?
Yeah.
Okay, so I'll give you 2 minutes, or I'll give you 5 minutes. You can try solving this equation. हेलो, हाँ सचिन, कॉल आया था यार।
हाँ, बात हो गई उन लोगों से?
हाँ, उन लोगों से हो गई सर, वो लोग कोलैबोरेट करेंगे शायद।
वो आए थे लैब में?
हाँ, आए थे, आधा एक घंटा रुके,
सही है।
और सर ने बोला है कोलैबोरेट करने के लिए।
अच्छा, वो लोग करेंगे क्या उससे कोलैबोरेट?
हाँ, उन्होंने बोला है।
नहीं, वो करेंगे क्या?
उन्होंने वो लोग सिमुलेशंस करेंगे, वो हमारा डेटा लेंगे और हमें ऑथरशिप देंगे।
सही है, वो लोग सिमुलेशंस करेंगे।
हाँ, हमारे कौंडूरी सर को थोड़ा सा वो दग दग होने लगा।
कौंडूरी सर भी थे क्या?
हाँ, कौंडूरी सर कह रहे बहन जो मेरी जॉब कहाँ गई।
तो कौंडूरी सर के साथ करना ज्यादा अच्छा है ना, उनके साथ क्यों कर रहे हो?
नहीं, कौंडूरी सर के साथ ही करेंगे, बट वो जो रिड्यूस ऑर्डर मॉडल और ये सब है ना, मॉडलिंग वाला पार्ट, तो हम लोग उनसे क्या कहते हैं वो करना चाहेंगे। और सर भी बोल रहे थे कि बढ़िया हम इनसे कोलैबोरेट करेंगे, ताकि हो सकता है तुम्हें पोस्ट डॉक अगर तुम्हें वहीं मिल जाए तो।
सर बेटा ऐसी गोलियां देते हैं सर, सबके पीछे पड़ना पड़ता है सर, गोलियां देने में बहुत माहिर हैं।
अच्छा मैं
बोल के फिर भूल जाएंगे उनको।
पढ़ा रहा हूँ, मैं पढ़ा रहा हूँ, ठीक है, मैं करता हूँ।
हाँ?
पढ़ा रहा हूँ मैं अभी NPTEL।
अच्छा ठीक है, हाँ।
करता हूँ अभी। Okay. So do you need more time, or shall we proceed? Okay. So let us start solving this problem. So okay. So the R dot for this equation, for this case, yeah. So the R dot can be calculated as 5.5 into 5 to the power 0.4, right? So if you solve this, you will get the value as 10.470 millimeters per second. Okay, so if you substitute this thing, so you know the length of the propellant. So if you divide 1 by 10.4700, and since it is in meters, you have to multiply by 1000. So you will get the burn time. Okay, so probably so you will get around 10.4. So you will get around 95.510 seconds. Okay. I hope this is clear now. So let me see the answers.
Yeah, I made some silly mistake with 5 actually. That A.
Okay. So let us calculate what is the mass generated. So the mass generated is the row of the propellant. This is 1750. Then pi into 0.25 into the diameter of the propellant. This is 0.5 meters into the, this is rho A and R, right? So you have to multiply 10.4700 into 10 to the power minus 3. So if you do that, you will get the value as 3.5976 kgs per second. Okay. Okay, so let us look into another problem, which is more related to the temperature sensitivity of the propellant. So it is given that the burn rate of a solid propellant is to be determined to be 10.5 mm per second at a nominal initial propellant temperature of 2500 degrees Celsius. Okay, and it is to be required what happens when the temperature reduces to 600 Celsius. Okay, so and it is given that temperature coefficient of a propellant is given. So this alpha T, you have 0.00420 Celsius minus 1. Okay, so you have to find what is the burn rate at 600 degrees Celsius. So any ideas on this, how to go ahead? So what is the definition of alpha T? So this is R dot d ln R dot by d ln T, right? I hope this equation you remember, right? Okay, so
Could you please elaborate a little bit, like where has this come from?
okay, so this is the just a definition. So what we are saying is, so if the temperature increases, right? So what happens, the chemical reactions becomes faster, right?
Right, right.
Why? Because if we can express this thing in Arrhenius rate law, which is delta minus EA by RT, right? So reaction rate is just A exponent EA by RT, right? If temperature increases, this term okay, temperature increases, this term, okay, this is this term reduces, this exponent term increases, therefore the omega also increases, right? So the chemical reaction rates become faster. So we so uh, the temperature dependence um, okay, the reaction rate dependence on temperature, the reaction rate dependence on temperature is given by, so whatever term that we have here is given by temperature coefficient. Okay, so this is known as temperature coefficient. So it depends on the composition of the propellant. Okay, so which is given by, this alpha T is given by 1 by R dot d ln R dot by d ln T. Okay, so to calculate this alpha T, experiments are done at two different temperatures, say T1 and T2, for which we get R1 and R2 as a burn rate. Say if you are getting R1 and R2 as a burn rate at temperature T1 and temperature T2. Okay, so this is alpha T is just 1 by R1 ln R2 minus ln R1 divided by ln T2 minus ln T1. Okay, so this is how the temperature coefficient is defined. Okay, I hope this term is uh, this equation is clear to everyone.
So this one is actually talking about the change in burn rate with respect to temperature.
Exactly, yes.
Okay.
Okay, so if you have a propellant that is at a higher temperature, so we expect that it burns faster, right? So
Right, right.
so if we are say so so if we know the temperature, say if we know the temperature of uh, say Sriharikota, okay, and we know the average temperature what we have, okay, so and say our propellant is made somewhere, say in Russia or somewhere where the temperature is lower, and if we design our rockets based on the burn rate that they have observed, will be very less, right? Because they are near to this pole, okay, north pole, so the temperature are colder. So if you come to the equatorial site, so we'll be having a different burn rate. So to have this to characterize the dependence on the temperature, we have this parameters which is known as temperature coefficient. Okay, so let us try to solve for this. So it was given that the temperature coefficient is given, which is given as 0.0042. Okay, and the burn rate at 2500 we know. Okay, so this will be, and we know this. So this is, so I have taken minus sign uh, from the top and the bottom common, so that's why we have taken it like this. Okay, so this is ln r2 minus ln 600. Okay, so if you solve for this ln r2, so you will get r2 as 9.8859. so let us tabulate this. This is at 600 and r1 is 10.5, which is at 2.90. okay, so this is what this parameter tells you. Okay, any doubts on this?
Could you please tell a little bit more about the unit of alpha T? Why is it per degree Celsius?
Okay, so what we are doing is we are normalizing this term, this burn rate uh, with uh, with itself. So it's just so whenever we have, say if we have a temperature, say 298, okay, we can have any standard reference temperature, right? So at
Right.
reference temperature, the mhm, okay, uh, yeah, so um, okay, so it will be at reference temperature. mm, 1 minute. So I think it is just a way of how we normalize, right? So whenever we have something like thermal expansivity, right? That is
Yeah,
also 1 upon how much volume is changed with respect
means
to
initial volume or initial length. We
uh,
normalize it with
so
that
we are just
initial quantity.
normalizing, right, with
Yeah.
the initial thing. So this is what, so probably it is useful when we are comparing two different propellants, how they are responding to the different temperatures. Okay, so if you have different propellants, so how sensitive they are to the temperature can be represented by this equation. Okay, when you divide, so probably you are just normalizing with the initial burn rate.
Uh, is there any like simple reason why this logarithm is coming up in this definition? Is it because of the Arrhenius exponential?
Uh, Probably yes. Right now I am not sure, but yeah. So
Okay.
it could be a reason for that. Yeah. Okay. So right. So let us move to another problem. So it is okay. So we have four. Uh, okay. So we have a double base homogeneous propellant known as cordite. Uh, we and the density is given, C star is given, burn rate is given, so and the diameter is given, right? diameter is given, and it is given that cordite is used in missiles, and it creates a thrust of 500 newtons over a period of, so this is TB, this is thrust, and this is diameter. Okay, and this is the C star and the density of the propellant. Okay, so and it is also given C, coefficient of thrust is given, and we are required to and it is asked what is the specific impulse for the missile. So probably this is easy, right? You can, so so first part is easy, right? So you can calculate what is the ISP. So would you, anybody, would you like to give it a try? How will you calculate ISP? Okay, so ISP is just C star into CF. Okay, C star is given and CF is given, right? So this probably we have learned during the initial classes, right?
Yes, sir.
Okay, so if you multiply this, you will get 1750 into 1.2, that is 2100 meters per second. Okay, so next is mass flow rate through the nozzle. So how will you calculate? Okay, think. Can we use, correct? You're correct. So the thrust is given as m dot CF into C star, right? And this is ISP. So you know thrust, which is 500 newtons, and we have 210 meters per second, right? So m dot we can calculate, which is 0.2380 kgs per second. Okay, next is burn rate of the propellant in mm per second. So how will you calculate? How will you calculate? This is slight tricky, but not at all difficult.
We have to find PC first from the C star definition, and
Okay,
then apply this St. Roberts 3.3 into
so do you,
PC to the power 0.3.
okay, C star is P naught KT by m dot, right?
Yeah.
So do you know the throat area?
Oh, that is not given. Yeah.
Okay, so could you try another method? And it can be assumed that this is a end burning ray. So probably if nothing is given, you can use as end burning ray. Okay.
From the mass flow rate and the area, we can determine the R dot.
Yeah, correct. So we have yeah. So the mass flow rate is given by rho of the propellant, area of the propellant into R dot, right? So the mass of the propellant, mass flow rate is given 0.2380. Density is given. So area is of the propellant you can calculate using the diameter, which is 0.325, and then the R dot. If you calculate this R dot, you will get the value as 1.640 mm per second. Okay. So next thing is burn rate of the propellant. If the burn rate of the propellant is 6 mm per second, what is the chamber pressure? So can you calculate? So can you calculate the chamber pressure? It is straightforward, no? This R dot is 3.2, P is 0.3. R dot is given as 6 mm, which is 3.2, pressure 0.3. So if directly you can calculate pressure, which is 8.128 megapascals. Okay. So let us discuss another problem. So yeah, consider a solid rocket booster uh, with a hollow cylindrical grain. Okay, we have a hollow cylindrical grain now. Okay, not concentric, but okay. Okay, so it is burning in the radial direction. Okay, so we have ISRB. So the density is given of the propellant, the length of the grain is given, length is given as 1 meter, and the burn rate is given as 7.5 millimeters per second. Okay, the outer diameter is given as 1.2 meter, and the inner diameter is given as 0.4 meters. Okay, if the initial thrust generated by SRB is thrust is given, uh, CF is given, chamber pressure is given, P naught. Okay, so it is asked what is the throat diameter of the nozzle. Okay, so how will you calculate? Any idea? How will you calculate
From the definition of CF,
CF? Huh?
yeah, CF is equal to PC80 by F, the actual F. Yeah.
By, I think it is thrust, no? No, it is the other way around. So it is thrust.
Sorry, yeah, F by
Mm,
PC80.
yes, thrust by P naught 80. So you calculate 80 from here. So this is okay. This is 25 kilonewtons divided by 1.11 into 3.5 into 10 to the power 6. This is 80. Now the diameter is just equal to pi d square into 0.25. If you calculate diameter of the throat, you will get as 90 mm. Okay, I hope so. Yeah, so this part is clear, right? So what is the okay the okay uh, we have the answer, but okay, the mass generated in SIB. So okay, so why it, okay, the answer is already there, but why it increases with time? The mass generated in solid rocket booster. Okay, first of all, let us answer why whether it increases, decreases, or remains constant. and if it is decreasing or if it is increasing, why it is happening. Okay, so let us try to answer this. So the mass generated is just rho of the propellant, A of the propellant into R dot, right? So the pressure is constant inside the chamber, so the R dot is fixed, right? Density is fixed. We have to see whether if a area of the propellant increases, the burn surface increases, the mass flow rate should increase, right?
Right.
So so at initially we have area this which is given by say A1, okay, and this is A2. So when it burns, the area increases, right? The exposed surface area, correct? So in ignition happens at the inner surface, then the flame travels, the the flame front travels along the radial direction to outward, right? Which increases the temperature, which increases the area, right?
Yeah.
So this can be written as area at any time is pi, this is okay. So if it is the length like this, no, so this is pi 2 pi rl, and l is, so this is the area which is that you see, right? So this is 2 pi rl. So m dot is equal to rho of the propellant. A area can be written as 2 pi rl into r dot, okay. So so as you can see, as radius increases, the m dot also increases, therefore the mass generated in the solid rocket booster increases, okay. So
I have this one
uh,
question related to the PC.
what?
So as the area increases, the port diameter, the
Yes,
volume of that port is increasing, right? So
yes.
will the PC remain constant or it will go
uh,
down?
yeah, so so it will increase actually. The PC will also increase because the throat diameter, unless and until you are changing the throat diameter, the uh, the 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 mass flow rate that is getting stored inside this volume will increase, right? And this will increase the
Yeah.
pressure.
Okay.
So that's why we have some progressive burning. So again, this area is increasing, p pressure will increase, the temperature, the thrust will also increase, you know. So because
Yeah.
thrust is given as cf into p naught into at, right? So if p naught is increasing, so the thrust will also increase, so we have this progressive burning, progressive. So pressure increases with time, okay. So in case if we have a propellant that burns from outside towards inside, so initially the pressure will be higher and it will gradually decrease, okay. So we'll be having a decreasing trend.
So can we make that conclusion from the value of n in this particular example?
Value of n,
Yeah.
where is n given? N is not given, no.
Okay. Okay.
It is given that burn rate is this.
For n, we need both a and n. A as well.
Yes, yes, okay. So the type of burning in SRB again, so I answered it, so it is a progressive burning, right?
So in case of n burning grain, in that particular case, this should remain constant, I guess.
Which one?
If you consider n burning grain,
Ha.
the area of the port will remain constant.
constant. So we have a neutral burning.
Okay. Okay.
Okay. So let us look into another problem. We have a propellant that is having a some star structure. Okay. So initially the area is higher, no, and when it burns it becomes a circle. Okay.
Yeah. Yeah.
So from this area to this area we have a regressive burning. Okay, but again after when it becomes complete circle it goes out, and it again becomes a progressive burning. Okay, so the graph will be something like this. So decreases and then increases. Okay, so let us look into another.
So it will decrease up to the vertex, up to the point the burning ends
So
at the
initially
vertex,
it will
right?
be higher, it will be very high, because you so this
Okay.
type of things are used in a real rocket engines, where you need um, higher thrust in the starting. So because your initial mass is more, right? So if
Okay.
you increase this area so that the pressure increases
Okay.
rapidly, and you have a thrust, then you can decrease. Okay, then further you can increase when you have say left the dense atmosphere, then you can accelerate faster.
Okay.
Okay, so next is initial mass generated generation rate of the solid rocket. So the r so initially what area you will be having, the inner area, right? Okay, so that will be 2 pi r1, that is the inner radius, into length, this is the area, then density of the propellant into r dot. Correct? This is the initial mass that will be generated, no?
Correct, sir.
Okay, so if you substitute this, what you will get the value as 16.022 kgs per second. Okay, so next is uh, the mass generated in the combustion chamber at the burnout. So at the burnout the flame will be somewhere here, no, at the outer portion. So it will be 2 pi r outer into L into density of the propellant into r dot. So if you substitute this radius, so you will get 48.0663 kgs per second. Even I can modify this problem, and I can ask what happens, what is the mass flow rate at time t is equal to, say 2 seconds. How would you calculate this? If I would ask you what is the mass flow rate at time t is equal to 2 seconds, then how will you proceed?
Determine the radius at that particular time.
Yeah, right. So what you will do is, you know what is r dot, right? So after 2 seconds, the surface would have proceeded with 15 mm, right? So
Yeah.
initially this surface will be 0.4 mm, and then after 2 seconds it will be some 0.4 plus some 15 mm, right? So
Right.
then based on this you'll get the instantaneous radius, and then you can calculate what is the mass flow rate. Okay, so let us look into the last problem. Maybe I'll not solve it completely. Okay, yeah, maybe the seventh I can solve. Yeah. So the sounding rocket uses a composite propellant with a star grain configuration. Okay, the star gain has a 6 vertices, okay, with an initial side of 0.2. So it looks like this. So let us make 6 vertices first. 1, so let us make these 1, 2, 3. Okay, these are 6 vertices. 1, 2, 3, 4, 5, 6 vertices. This is the center. Okay. So we have 6 star gain, okay, 6 vertices, and the length and the side length is given as 0.2 meters. Okay, density is given, length of the propellant gain is given, burn rate is given. So okay, so you have to find what is the initial burn surface area. So how will you calculate? So how will you calculate this surface area, burn surface area?
Perimeter into length of the rocket.
Right, so perimeter is, you have 2 into sides into L, right? So this is 2 into 0.2 into 4. So this is so the number of sides, okay, number of sides is, we have not multiplied. Okay, 2 into number of sides into, yeah, so this is into 6. Okay, because 0.2 we have 2 of such thing that makes 1 vertex. Okay, and there are 6 vertices and this is the length, so this is 0.96 meter square. Okay, initial mass generated, then how will you calculate? This is the area, right? Area is equal to density of the propellant r dot, okay, this is m dot. M dot is density of the propellant, r dot into heat, this, so this is 1650 into 0.96 into 8.5. so you will get the value as 13.464 kgs per second. Okay, so yeah, so any doubts on this? Any doubts till so far? So there is another problem, probably you can try, you can buy it yourself. Okay, so okay, so now we have a rocket that is having a square slot. Okay, this is given as 3 meters and the outer diameter is given as 1.2 meters. So the throat diameter is given, okay, this length, I think the length is given, So this is 0.6 meter, 0.6 meter, this is 3 meter. Okay, so the linear burn rate r dot is given, uh, then the density is given, and c star is given. Okay, so determine, first of all we have to find what is the web thickness. So what is the web thickness?
Minimum thickness between the motor case to inner propellant, sir.
Right, so the minimum will be this, no? No, this.
Here it will be a cord, sir.
This one, no?
Correct,
Yeah.
sir.
So this is the web.
Correct, sir. The minimum.
This will be minimum. Okay, so how will you calculate? So this is this problem requires geometry, complete geometry. So this is the diameter, this is the radius, which is 0.6 meters. Okay, now this is, so what you can do is you can first calculate what is this thickness, right? What you have to do is you have to calculate, you can use Pythagoras theorem and calculate what is this distance, and you can subtract by the diameter, by the radius. Okay, you will get the web thickness. Okay, so the initial burn surface area is also simple, it is just 0.6 into 4 into the length. Okay, then maximum surface area, how will you calculate the maximum surface area? Okay, so the maximum surface area happens when
Okay. 2 meter given, sir.
what?
Diameter given 1.2 meter.
um, no, this is the initial surface area, so this will be 0.6, this will be perimeter, no? 0.6 into this is the perimeter, and this 3 meters is the length. Initial surface areas, it is asked. So the this will be the initial surface area, no? This is the perimeter and this is the complete.
The maximum burning will occur when that sphere has reached the
Right,
vertices have reached the outer diameter.
yes. So this will be, okay, this will be this, no? Correct, no?
Yeah, yeah.
Okay, so how will you calculate this? So this is just a
Pythagoras again.
again geometry. Yeah, this is the diameter. Okay, uh, then yeah. So what you can do here is, um, so mm, okay, so probably the mm, okay, I think this will be something like this. This is not the this will not happen, right? Mm, actually, the corners will proceed like a semicircle, right?
Okay. Yeah.
So
At last there will be some sliver mass. Yeah.
yes, correct. So this is the initial, right? And the corners will become like this, right?
Yeah.
And this again will be equal to a. This is a. This is a. And this is a. And then you will be having surface area like this. Correct?
Yeah. Correct.
So maybe I'll draw it properly. So this is A. So so um, so how to calculate this area, this parameter? You have to calculate this parameter, this, then this, this, and this. I hope you are able to see, right, this what I am drawing. So this this part you have, this is what will look like. Okay, so to calculate this perimeter, what you can do is, this is what I have done. There can be different ways of doing this. So what I have assumed is this, let us, this thing is theta, this is A and this is D, right? So the theta will be sine inverse of A by D, correct?
Yeah.
So the perimeter will be 4 times of theta, because we have 4 such angles, correct? 4 times of theta divided by, if you are using theta in radians, then it will be 4 by 2 pi into 2 pi r, right? This is the complete perimeter of the circle. Okay, but we are taking into this factor into account. Okay, I 1 minute. So this theta will be, not this, actually this will be the theta. So this is theta dash, correct? So okay, how to calculate theta dash? This is just pi by 2 minus, this will be also theta, this is 2 pi. Okay, this will be equal to theta dash. Okay, so first you have to calculate this theta, then you have to calculate this theta dash, which is this angle. Okay, then what you can do is you can find the perimeter of this part using this relation. Okay, therefore the net perimeter will be equal to 4 into theta dash divided by 2 pi into 2 pi r plus in the 4 sides 4a. Okay, so the net area will be 4 theta dash, 2 pi will be cancelled. Okay, so it will be 4 theta dash r plus 4a into the length. Okay, so if you substitute this, so theta, what on theta you will
Can
get,
we think of it in a simpler way, like theta prime is the angle,
yes,
so the arc length is simply theta prime into r,
yeah,
if theta
anyways we
prime
have
is
to
in.
calculate this theta prime, no?
Yeah, means instead of doing
Okay,
this,
this part, yeah, this arc length into r, yeah, that's true.
arc length is directly equal to theta prime into r.
Theta
We
prime
can
into r,
think in,
correct,
yeah.
correct, yeah, you can do it
Okay.
in this way also. So I hope this calculation is clear, right? So if you calculate
Yeah.
this theta, so let me see my results. So yeah, so I'm getting theta. Okay, and I am having, sorry, I'm having the final result. So the area is 10.9699 meter square. Okay, so I hope this is clear, right? This calculation part is clear, right? So this maximum burning surface is, I think you might have understood, right? So now the thing is, sliver mass. What is sliver?
The remaining mass that is unburnt.
Yeah, so this is this part, no, into 4, because we'll have here also. Okay, correct, no? So you know this A, you know the diameter. Can you calculate the area within the chord? Okay, so I'm just giving the idea how to calculate this. So you can calculate this area, then you have to multiply by the length and by the density of the propellant. So you will get the this, if this is area, and into 4. So with this you can calculate what is the not m dot, it is m. So what is the mass of the leverage? I hope it is clear, right?
In the previous question for maximum burning surface area,
uh,
how have we calculated the A, small a?
Small a will be equal to this a, no, this 0.6. So it will proceed in linear direction, right? The surface always propagate normal to itself, right?
Okay, okay. Only the corners will become.
On only the corners will become semicircle.
Okay, so initial that square's edge will remain same until the last point.
Yes.
Okay.
Okay. Yeah. So okay. So you understood, right? This part is clear, right?
Yeah.
Okay. So the next thing is leverage mass is this is also clear, right? The calculation part. So what you do is you calculate what is this angle, this area, then you know area, you know diameter, you can calculate the area of this part. You know, you can calculate the area of this part, correct? And you subtract these two, you'll get the area of this chord, and you multiply with 8, you will get the total area, right? And you multiply with the length and the density, you will get this leverage mass. Okay, I hope it is clear, right? Any doubts? Any doubts on this? Okay, so okay, so probably I'll stop here, and if you have any doubts, please let me know.